So the new experiment for this year was a thermometric titration. And it's kind of like this because it was a combination of two experiments that you'd done as part of the spec, but put in together in a sensible, fun experiment. So before we go into the thermometric part, let's remind ourselves of what an acid-base titration is all about. At a nice simple level, you're going to take a strong acid, so that's a hydrogen with an anion, a strong base, that's cation with hydroxide, the H plus, the hydroxide come together to make water, and leaving you behind with the salt. That's the reaction, the neutralization reaction you've learned so much. So when we do a titration, we'll take a conical flask, we'll mount above that a burette, and in one we'll put an acid, the other we'll put a base. This particular one, I'm going to put the base in the conical flask, and I know the concentration of the base, and I know how much base I'm putting in there. And then I'm going to fill my burette with the acid, and I don't know the concentration of the acid. And one of the experiments that you do is we'll use a titration in order to determine the concentration of the acid. Well, hopefully you remember how you did that. The year 13 way is that you measure the pH against the volume that you're adding of the acid. You can use an indicator if you want, but by year 13 you're hopefully using a pH meter. And so when you start doing that and plotting it, you get a curve that looks like this. Start off nice and high because you've got a strong base. If you add the strong acid to it, pH goes down, 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 and then swoops on down until you're back into an acidic pH. Now, of course, halfway down the swoop is the so-called equivalence point. That is where you've added exactly the right number of moles of acid to neutralize all the moles of base. Now, because this is a strong acid, strong base titration, at the equivalence point, there's nothing interesting left. So the pH is 7. But what we're more interested in this particular case is not so much what the pH is, although we can use that to guide us for where the equivalence point is, but what is the volume of the equivalence point? Because that is the volume of the acid of unknown concentration that we've had to add to neutralize all the moles of the base. And so you set up a nice little relationship. Concentration of acid times volume of acid, so moles of acid is concentration of base times volume of base. That's the moles of base, because you know the blue, the volume of the base, the green, the concentration of the base, the purple, the volume of the acid that you had to add to get to the equivalence point. You can determine the concentration of the acid. So you've done that, I trust, ad nauseam. You probably did it in year 10 or 11, in which you used an indicator to indicate approximately where the equivalence point was. But the important thing was you figured out what the volume of the equivalence point is, how much of the acid you had to add to neutralize all the base, and because you knew how much base you had, you could work out the concentration of the acid having measured that volume. Hopefully I've repeated that enough. Now, in a separate experiment, you determined the heat change of a neutralization reaction. You determined that it was an exothermic reaction, that heat is given off. And so if I was to take that little neutralization and just open the tap of my burette so it drips in for acid into the base and measure the temperature, I would see something like this. So here we are, a little below 20 degrees. For 12 seconds, and I opened the tap for the burette, and a little bit was added, a little bit was added, a little bit was added. And as all the neutralization happens, we're getting heat given off, because every time one of these reactions happens, you get a little bit of heat given off. And so, ignoring a little blip there where presumably I knocked the bench or something like that, the heat continues to be given off until you hit a maximum, and then it starts going down again. And that maximum is where now no more heat is being given off, but the whole system is just cooling down. Now, we could do this in terms of time, but seeing as how what we want is we want the volume of the equivalence point, what you're going to do in this experiment is you are going to measure the heat temperature change associated with the volume added. So we're going to get a graph very similar to this, temperature going up the vertical, but along the horizontal, it's going to be the volume added. So how do we set it up? Well, we're going to do a thermochemistry experiment, so we're going to use the extremely sophisticated scientific apparatus of coffee cups, put them inside a beaker just for stability, mount a burette because we're going to do the titration into the coffee cup, and clamp a thermometer so it's about 1 inch from the bottom. If you have a lid, put it on. So this is what the best apparatus would look like. There's the beaker holding the 2 coffee cups, there's the lid, hole in the lid for the thermometer, which should be down in there to almost to the bottom of the solution. 1 inch might be a little bit too high, and there's our burette going in there. Now actually, when we did this experiment, we didn't bother with the lid because it's much easier to stir consistently without the lid, and it really didn't make a whole amount of difference. So there's the actual apparatus we used. We're going to measure into the cup 10 cubic centimeters of the sodium hydroxide solution, so that's in there, and we know the concentration of that sodium hydroxide solution. So this is exactly like we did for the acid-base titration. And then we're going to wash the burette correctly and fill it with HCl solution, the concentration of which is unknown. Now, do be sure that you use correct technique when you're filling a burette. That is, you should never, ever, ever be reaching above your eye level to the top of the burette to pour in the solution. And of course, you always wash it first, which means simply that you put some of the solution in the burette, you run a little bit out into a waste bottle, and then you upend it, opening up the tap while you're doing it, and sort of rotate it around, turn it around as that solution is pouring out again, hopefully into the beaker. Anyway, then once you've got the temperature of the sodium hydroxide is stabilized, record it, add a little bit of HCl. This prep, and it's probably good enough one for what you might do on an exam, is 2 mils of HCl. I did it with much smaller volumes of HCl, but 2 mils of HCl will work. Swirling the cup gently or using a stirrer, and the temperature will go up, and measure the highest temperature attained as it went up. And as soon as it starts going down again, add a little bit more HCl, swirl, record the highest temperature, and keep doing that until we reach a point at which the temperature is no longer not going up anymore, but it's going down. And we say here 3 successive additions have not raised the temperature. You really need to get a decent set of data past the maximum, and you'll see why in a minute. And anyway, then we're going to plot, as we said, the temperature against the volume. Now, here's my data that I got using 10 mils, 1.5 molar sodium hydroxide. You don't need to do anywhere close to this. And of course, 5 decimal places even is ridiculous for the temperature. But I used a fancy little probe rather than the thermometer. I also used a little drop counter rather than just a burette for the volume. But the idea is the same, except you'll probably have maybe 1 mil additions, possibly even 2 mils additions. It depends on how you'll set it up. But anyway, we'll take these data and we'll plot the volume against temperature. We get a lovely curve that looks like this. And you can see that, of course, as we start adding it, the temperature goes up, 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 until we crest, because by this stage all the neutralization has gone on and it cools down. Now, what the unwary student might do is say, oh, here's the peak. This must be the volume of the equivalence point. But the trouble is that as you're adding the HCl and heat's being given off, the system is also cooling down. And so what this curve is here, going up to the maximum, is it's a combination of heat being given out and cooling down. So as I hope you did for a previous thermochemistry experiment, you don't believe the top here. Rather, you draw 2 straight lines. Now, the first straight line is you just try to follow the curve at the start here, the increase of the curve at the start. So this is what the temperature increase would have been if there was no cooling. And you can see here we're starting to cool away there. Okay, and then this, of course, represents the cooling when there's no heat being generated. And you can see, I hope it's a lovely straight line there that we can draw that pink line for it. Okay, so the idea here is that if there was no cooling going on, the maximum would actually have been here rather than all the way along there. And it's where these 2 lines intersect, right? The straight line that you've drawn trying to mimic the increase at the start of the species, the straight line that you've drawn to try to get the cooling interaction going. It's that intersection that corresponds to the equivalence point. And for my particular experiment I did here, it happened at 8.2 mils. Calculations are trivial. We had 10 mils of 1.5 molar sodium hydroxide. That's what I measured out with the pipette. That's what was on the bottle. And from there, I can calculate that I have 15 millimoles of sodium hydroxide. Much easier to say milliliters times liters, cubic decimeters, to give you millimoles than it is to say, well, this is 0.0100 liters times that. Just makes the calculations easier, I believe. Well, anyway, we found out that we needed to neutralize those 15 millimoles of sodium hydroxide, 8.2 mils of the HCl, for which I don't know the concentration. And of course, the whole point is it's a one-to-one reaction. So the 15 millimoles of sodium hydroxide were neutralized by 15 millimoles of HCl. 8.2 mils of the unknown concentration HCl contained 15 millimoles. So now we can just put all that together. The concentration X is the number of millimoles, 15 millimoles of HCl divided by 8.2 milliliters. Now I hope you can see that the milli on top will cancel out with the milli on the bottom. So this is actually calculating for me moles per litre or moles per cubic decimeter. But if you'd feel better, you can convert the millimoles to moles, so that's 0.015 moles. You can convert the milliliters to litres, 0.082 litres. Either way, same thing. And my particular result gave me 1.8 moles per cubic decimeter. Do watch out for sig figs as well when you're doing these calculations. Hope that was clear. Hope you enjoyed the experiment. And good luck with the exam.